It's a perfect note for starting because it is now 5:05. So, welcome. We'll introduce ourselves as well. So, I am Michelle D'Arienzo, and we also have here Amanda Horn. We work together as educators at Brookhaven National Laboratory. So, we specialize in sharing the cutting edge science going on at the lab to teachers and students all across the country. We do this both virtually and in person, depending on location. And we do this through hands-on activities, workshops, contests, trainings. We do a little bit of everything. So if you are not familiar with Brookhaven National Lab, that's where I'd like to start. So we are located, if you're local, if you're from Long Island, we're off the William Floyd Parkway. For those of you that are not from Long Island, so if you imagine the fish that is the island, we're just right before those tails start on toward the eastern side. So we are an entire town. We are 5,000 acres. So we're the whole town of Upton, New York. And within that town, there are different science facilities, and they're all working together toward new developments in science and engineering. So some of the highlights here, because to talk about everything would be impossible, are the relativistic heavy ion collider. So that's up here where it says the atom smasher, where they are in the process of actually upgrading to something newer called the electron ion collider over the next 10 years. So your students now could be employees working on that in the future. And what they do there is they study the conditions found in the early universe to gain a deeper understanding of matter, energy, space, and time. And they do that by smashing atoms together. Then we have our other big circle. We have lots of big circles at the lab. And the bottom right here, that's the National Synchrotron Light Source 2, where anyone, and I mean anyone, we have high school students doing it, anyone with a good idea can submit a proposal to put a sample, so anything you want, in one of the brightest beams of light in the world. And they do that to uncover things like atomic structure, elemental makeup, electronic behavior, pretty much anything you want to know that's on the like super tiny scale of just about atoms. Another one of my favorites is over here, the medical isotope maker, the Brookhaven linear isotope producer, where many of the isotopes needed for medical imaging and treatment for the entire country are made. And they're also developing new technologies that will improve imaging and treatment for things like cancer, heart disease, anything where you're going to need to be able to see in your body or remove something that doesn't belong using radiation treatment. So those are all being developed there. And with some other national labs across the country. We have, let's see, what's another good one? This one, the Interdisciplinary Science Building. Their scientists and engineers of all different science backgrounds are working together to create and test new technologies. And the idea is to meet the nation's growing energy needs because our lab is run by the Department of Energy. Um, and then the big one that I want to point out is what used to be actually the National Synchrotron Light Source. This was the original one. That is our computational science initiative, and inside of there is the Scientific Data and Computing Center. And they, along with our IT team, who help our staff develop coding that enables them to perform their research quickly and efficiently. So I really just wanted to point them out. Now, one problem there is that every single one of the scientific disciplines and engineering as well that happens here needs computer and coding skills. We are constantly hearing that they love interns that come in with these skills. So that makes it really important that students should come in with a foundation in this. So in fact, last week I searched for computing on our job page and I actually found 68 different jobs that are looking for someone with some kind of computing experience. So it's really important to us and to the country as a whole because there are actually 17 national labs. So we're just one of those. They're all run by the Department of Energy, and they all have similar job opportunities, and they share the same goal of training the STEM workforce of the future. So getting everybody comfortable with coding is really, really important to us. So our specific group at the lab is called the Office of Educational Programs, and we provide educational content and experiences for K-12 students, teachers, college students, college faculty, and even postdocs, so people who have finished their doctoral degree. So for the K-12 sector, that's where we are. So we're the pre-college side. We offer field trips, contests, summer programs, research opportunities, and teacher professional development. So that website that you see up on the screen is bnl.gov/education if you want to learn more. So enough about that. What we really want to talk to you about is that this summer we did a teacher professional development that was a pilot program funded by the Department of Energy, and we ran it over 4 weeks this past summer. And Amanda's going to tell you a bit more.
Hi, everyone. Thanks for the intro, Michelle. So what was really great about this program is that not only did we get to spend 4 weeks with these teachers, but this was a program where they were given a stipend. So if this is something you're interested in, we definitely want to just put that out there. But we had a few goals, and obviously that stipend was one piece of it that was important to the teachers, but we were also hoping for these teachers to take some things back with them. We wanted them to develop a familiarity with BNL and DOE's scientific mission. As you just noticed when Michelle was talking, there's a lot of different science that we do at the laboratory, and we want to make sure that teachers are aware of it and are sharing the science with their students and the opportunities that go along with it. But not just our lab, we are multidisciplinary and we do hit quite a few different disciplines of science, but the science is happening across the nation as well. So in addition to that, we were hoping for the teachers to learn simple computer code and gain a proficiency with the technology and hardware. So Michelle and I are going to actually demonstrate or show you two of the different pieces that we showed and did with the teachers this summer. And we were hoping that they would take this back into their classroom to their students and be able to share what they had learned with them. And then on top of that, they were designing and piloting a lesson module that was centralized around DOE science to be implemented in the classroom. So during those 4 weeks, they developed this lesson and actually got to demo it with some rising 10th grade students that we had in one of our summer programs. Okay. So that overview. So how do we break down those 4 weeks? So the first week, we had the students familiarize themselves with BNL. They went on tours. We had several different speakers from across the laboratory come in, and they focused on learning the basic computing skills needed to collect data about climate and atmospheric sciences. After that, weeks 2 and 3, they continue to learn additional computing skills, in addition to modeling, data analysis, and applications of the data used. So during these weeks, they were actually using some different sensors, which you're going to learn a little bit more about from Michelle, and taking those sensors outside into different environments and collecting data, bringing that data back, and we worked on how we can model and analyze that data. And then finally, week 4, they took some of those lesson modules that they had developed and tested that with high school students and then made improvements based on that experience.
So I'm going to start out with kind of the coding and electronics part. So we started the whole session, we started the whole weeks with just let's get these sensors working. So I'm going to tell you about some of the sensors we use and kind of guide you through that process. Because if you can take just the code that I talked to you about, you can actually take it and make it work with any sensors that you want. And of course, if you need help along the way, we'll put our contact information toward the end of the slides because nothing works perfectly the first time. So we're happy to help. So we chose sensors for our workshop because they were relevant to weather and pollution, but there are tons of sensor choices out there, and there are actually several vendors that make them. So we chose to introduce sensors from 2 major brands because they're super common and really easy to order from. We worked with Adafruit sensors and SparkFun sensors. That allowed us to introduce actually 2 different coding languages. So with the Adafruit, we were able to use Python, and with the SparkFun, we were able to use Arduino. And many of the sensors that you can buy can use either one of these. So you can choose whatever you're most comfortable with. So we're going to start with kind of one of the first ones we did. So we're going to do temperature, pressure, and humidity sensor, and that was from Adafruit. So that's going to be in Python. So to do this, you need a microcontroller. So these are like basically mini computers that can translate what you want to do with the sensors from Python code that you write on your laptop or computer. And the best part about these is that they're really cheap and they can work with Chromebooks, often with web-based interfaces. So the reason they're so cheap is because they're different than your computer. They only have enough processing power to run one small program for your sensor. But if you buy a laptop to work with or a computer to work with, that has what we call a central processing unit. And that is going to have a lot more memory and speed because it has to be able to run videos, games, websites. But we don't need to be able to do that. We just need to run a sensor. So because of this, if you have the processor on your computer, that's like half the cost of it. It's, hundreds of dollars. But the processor on a microcontroller only costs $1. So we can do a lot with not too much money. And I know everybody always gets excited about that. So once you put that chip together with all the connections and electronics that you need, you have a microcontroller unit, and that costs, from like $9 to $15, depending where you buy it from. So the SparkFun equivalent is just a little bit more money, but it's not much. It's under $15. So we're using the Adafruit KB2040. And if you are someone who's like really interested in computing in these projects, the little chip that runs it, that's actually a Raspberry Pi chip. So it's like those Raspberry Pi computers, but super tiny. Then we hooked it up to a sensor. So I like to choose the ones that have a quick connect system where you can just plug and unplug. So that way you can avoid soldering. So for Adafruit, that's called STEMMA QT. If you choose SparkFun, it's called Quick, but they work interchangeably. So we've actually traded wires back and forth depending on what we're going to do. So this one is on the more expensive side, but it's because it measures three different things. It measures temperature, pressure, and humidity. So if you know that you only need to measure temperature, you can actually save a ton of money and pick up a sensor that costs $4 or $5 instead. So we're not at too much money, and you can group students together, which is really great. So to get everything connected, you need a little under $30, but this price can actually go down to $20 or so if you choose a cheaper sensor. And we like to do this with a group of about 4 students. So you may not need, we typically buy 8. We like to buy 8 sets because we sometimes have bigger classes. But if you know your classes are smaller, then it's not too much. So do keep in mind that once you have all the wires and the microcontroller, you just have to get whatever other sensors you want. So, this could be any sensor. It could measure something totally different, like pollution. Why not? So the same setup, everything except this sensor can be used for anything in the future. So you just have to invest in running it the first time, and then you can just, slowly collect sensors over time. So you have some options. You can have the students write all of the code that they need themselves. You can supply most of the code, but leave a line or two missing that they have to type in. We very often do that with our students. Or you can just give them the code and have them look at it and go through it and run it themselves. And just seeing that process, they may be able to make some changes on their own. And that's what we found with the teachers in this workshop, that, by week 2, they were changing things without even talking to us, which was awesome. So the language we use to control this particular microcontroller is Python. This language is commonly used in science, which is why we used it. And it's becoming more popular in really most STEM fields as time goes on. And it's because it more closely resembles English than other coding languages, so it makes it a little bit easier to read, but also because it has so many built-in functions that can do the hard work for you. There are many different libraries or sets of code that you can use for science functions and for analysis functions. And just as a fun fact, the name Python comes from Monty Python's Flying Circus. The people who originally wrote this language were fans of the show. Now, we also use Circuit Python, which is basically Python with some additional commands specifically for microcontrollers and sensors. So things like turning an LED light on and off. So there's an entire website, circuitpython.org, that is filled with information about what you can do with CircuitPython and how you can use it depending on what microcontrollers or sensors you've chosen to use. So to write code, we used an interactive development environment, or IDE, called Thani. So if you don't know about IDEs, you can think of them like a text editor that will color code what you write to help you more easily write and edit your code. We did find, though, that Thani was a bit challenging to install on some school Chromebooks, but with a little help from your tech team, it's definitely possible. And I did find out after this workshop that there is an online Circuit Python, and that actually is a whole IDE of its own that you can run through a web browser. So if you really have a lot of trouble, we'd be happy to help you figure out how to use that in the future. So to be able to collect data and save it, what was that?
There's also an online version of Arduino that you don't need to download, which is
Yes, so you can use either type of coding that we used online. So that's really great because I know that's always a challenge. So to be able to collect the data and save it, we actually ended up writing two different codes. If you don't mind like writing the data yourself or typing it into an Excel yourself, you can do this with one code. But to be able to save it into a file and use it later, we added an extra code. So there's one in Circuit Python that's on that little microcontroller. So we like drag it on there as if it was like a thumb drive that you plug in. And then there's one from our computer. So the one on the little board will tell the microcontroller how to run the sensor. And then the one on your laptop sends the signal for that to work and then collects the data. So the one code on the laptop will send a signal, and then the little circuit chip will send information back to the computer for us to analyze. So now there's code on there, and I don't expect you to be able to read it right away, but try to follow along section by section with me. So the first chunk of code imports libraries. Those are pre-written code that can be called by name at any time. So that's built into Python and CircuitPython. The libraries we need let us control the circuit board or microcontroller, choose the color of the LED on it, communicate through the USB wire, run the sensor, that's the MS8607, and tell the board to wait, which is sleep. The second chunk of code sets up communication between the microcontroller and the sensor, and also from the microcontroller to the computer. So the USB CDC is actually sending the data from the pieces of equipment to the computer. The third chunk of code sets up the LED. It will turn it green so that we know everything is hooked up correctly. Then, and you can tell that it's green because on line 13 here, you have 0 red, 255 or max green, and 0 blue. These are RGB colors. So the next chunk is a function or section of code that, again, you can call by name. So whatever name you write here, if you put that later, it will know, okay, I want to run that section. That sends information from the microcontroller to the computer. So that sends it through the USB wire. Then the largest chunk is another function, and it can be called by the name read samples. So whenever we want to collect data, we run read samples. It tells it that we want to take 3 different measurements. We want to know about temperature, pressure, and humidity. We want to do that 10 times with 1 second between each time. And we want to send this number of measurement types, the 3, the number of data points, that's 10, and the actual measurements themselves to the computer. Then we want the LED to be red the whole time that this is happening. So that's why you have here the 255, 0, 0. So that's our signal that it's working. And then the last chunk of code says that the microcontroller should wait until it gets the signal to run. For us, we made the signal the letter R for run. Then it'll go through the code in the function read samples and turn the LED back to green. So it'll be green, it'll get a signal, it'll do all that big chunk of code, and then it will turn green again after it was red. So I know that was a lot, and here's another code. Don't panic. Don't panic, because we're going to give this to you. We actually have a Google Drive for you. This is all there, so you don't have to memorize it now. So this code is run from our laptop, and we run that through Thani. So the first chunk of code imports libraries, just like the other one. In case we want to be able to hold lots of information and do calculations with it, we import NumPy. We also want to be able to graph the values. This code doesn't actually do that, but we want the option, so that's matplotlib. And we want to be able to communicate through the USB wire. That's serial. The next chunk of code sets up the serial communication and opens it. So every time you plug something into your USB port, it actually gets assigned a port number. So in this case, you can actually see on line 6 that my port was called COM32. And this is something that you can actually look up in your operating system. So if you ever try and use this code and 32 is not the right number, you can feel free to email me and I'll help you out. The next chunk of code sends the run signal to our microcontroller. That's that letter R it's waiting for. It'll say the experiment is running. That'll do all its thing over there with its lights. It'll turn red, it'll take data, and then it'll send it back. So we'll know that's working if the LED turns red on our microcontroller. The next chunk collects information about the number of measurements, the different measurement types, the data points, all that stuff that it's supposed to be sending from the microcontroller. And it does set up something, it looks nasty, but it's not too bad. It's something called an array to hold the information. And you can think of an array kind of like a giant list of numbers. So it's a list of numbers you can call by name all data. So then the next chunk will read in the data as it's collected, and then it'll print out the temperature, pressure, and humidity for each of the 10 times that data is collected. And then this is the part, the whole reason why we do this separate code. The next section will ask for, oops, I'm one click behind here. There we go. The next section will ask what the location was. So input here is asking for what the location was. And we can save the data in a file called a CSV file. So that's what this chunk does. And that allows us to use it later. A CSV file can be opened in Excel or Google Sheets. You can even open it as a text file and it'll be a list of numbers. And finally, the last bit is closing communication with the microcontroller. So because it's really hard to follow without seeing it, I took a video of what this process looks like. So here we go. So I click run, and then it says experiment is running. My light goes red over here, and you see it's printing out data points. I have it set to do it every second so that the video is not too long here, but you can make it longer so you can do analysis over time. So at the end, it asks where you were. I was in my office, and it says office.csv is created so that it has saved the data. So then you have options for what you want to do with this data file. You could open it in Excel or Google Sheets, like I said, so that you can graph it there. That's what I did on this screen. I graphed it in Excel. The first column is temperature, the second column is pressure, and the last column is relative humidity. Or if you're feeling like going a little further with the coding and teaching your students a little bit more about the coding, you can very easily graph the data using that Python library that we imported called matplotlib, which we'll actually see how to use in just a few minutes. But before that, if my slide will advance, I wanted to tell you a bit about the ideas our participating teachers came up with. So they actually went out in the field. They had a blast. I love these photos. Special thanks to our teaching assistant, Kevin. I'm sure all of our teachers would love me to say that. So what they thought of doing is using a CO2 and VOC sensor to analyze pollutants from car exhaust. So they want to take their kids out, near a parking lot and check that out. Using that same sensor to analyze the air around a plant to see if they can find a difference in plant health based on the CO2 that it's giving off or the CO2 that it's collecting. Wow, that was backwards. Creating a weather station using several different sensors, including the one that I told you about today. Create a coding club at your school to teach students how to use the microcontroller. So we have one teacher who's just going through the basics, and then once they know what to do, in the future they'll do some projects on their own. Using the sensors to collect pollution and weather data on the Great South Bay. And our favorite, no offense to all the other great ideas that everyone had, but attach the sensors to a helium balloon to simulate a weather balloon launch. This was a fan favorite, I think. But the best part of this is that you can take the content that you need to teach anyway. And as you can see in these photos, if you add a little bit of that coding and you get yourself outside, you can have a lot of fun teaching something that you had to be teaching anyway. So it's just a nice new spin on things. So on that note, I'm going to hand things over to Amanda to give you an option in case you can't buy a ton of sensors.
All right. Thanks, Michelle. So those pictures you just showed, we had a great time going out with the teachers and even bringing our students out. I did a similar activity with the students and just bringing them outside and having them collect their own data. It belonged to them and their partner. And the excitement they got out of that it was a lot of fun to do it with them. But I know every time we bring any kind of cool piece of technology, I always get the feedback, What if I don't have the funding? And I know that these sensors are low cost, but that can still be a challenge for many teachers, many communities, and many schools. So this is another way to approach it. If you're looking to do any kind of coding work and you're in the climate area or environmental or earth science area, there is a ton of data that is open source and very easily accessible to you. So I'm just going to focus on one. Michelle will share a few more later. But I just want to make sure everyone knows there is so much out there that is published and pretty up to date. So some of the data you're going to see today is up to the end of 2022. So that was published less than a year later. It just came out about a couple weeks ago. So I'm going to focus on this NOAA database, the National Oceanic Perfect. So the Global Monitoring Laboratory, this is just one project that NOAA has. There are a ton more, but we're going to focus on this one. So if you go to the Global Monitoring Laboratory, and I'll be honest, I usually just Google that and this page will come right up. Right on their main page is this data tab. If you click on the data tab, it's going to give you a couple options there, so you can keep going. And if you click search for data, that's going to bring you to an entire search database they have within this laboratory for all the data they collected. And they collect a lot of different things, which is on the next page here. Anything from carbon dioxide, methane, all of these different options. You can see actually that second column has all of these different things that they are looking for. And that's just within this one laboratory. There's a lot more that NOAA actually collects through other laboratories and projects. So let's say we want to focus on methane. That's what we're going to focus on today. If you click on methane, and so you can keep going, Michelle, it will give you all of these different locations. You see that on this page alone, there's 266 out of 4,700. All right, so we're going to break it down even more because we're not going to go through 266 sets of data of methane. That'd be super cool, but it's going to take us a while. So what you can do is you can pick it by location. So our location for today, we're going to actually be using, we're going to start with the Mauna Loa location off of Hawaii. So if you keep going, Michelle. All right, so I clicked in, it actually, their acronym for that, they just use MLO. And now you can see I have 3 data sets. So now we've narrowed it down even more. So what they're doing here is they're collecting methane samples, really only using 2 different ways. They're using a flask collection or a surface PFP. But if you notice, even if we look at flask, for example, they talk about their frequencies. So for us, we're going to use monthly averages. And if you click on the data option here under monthly averages, it's going to give you a great text file of all the data they've collected during that entire project. So that project is still ongoing. This one was just, we just got the updated data from the end of 2022. But this data started back in 1984. Now, what we're going to do is we're going to look at multiple sites a little later, but we're going to first start with Mauna Loa. Now, this is a pretty unique location, as you can see very obviously. It is in the middle of the ocean. So it's going to have some different factors than what we may see here on Long Island or other places across the United States. Keep going. Okay. So this is the data. I opened up my text file and this is what I've got. So I'm going to give you about 10 seconds. Can you make any conclusions about the data you see on the screen so far? And this is only just a small chunk of the data. There is a lot more out there.
It gives me a headache. I can't draw a conclusion.
So I'm hoping you at least started to look at it. And I agree with you, Michelle. This is only a small piece of it. And if you look closely, this data actually starting in 1983, and the numbers next to the second column are talking about the month. So this would be May 1983. And the bottom of it is actually January 1986. So only a couple of years in there. And even just looking through that short period of time, there's a lot of numbers. And I agree with you, Michelle. I get a headache looking at this. We can be a lot more effective. If we're looking at maybe a change over time, for example, for methane levels in this location, we can use some code because, again, this is only a couple of years and this is going all the way to the end of 2022. So we're going to use code to help us. So you can keep going here. Now, if you want to do this yourself, you'll be using Thani, so the same exact program that Michelle just used before. And we're going to be using matplotlib. Again, one of the same imports that Michelle used already. So if you do Michelle's activity first, you'll be perfectly set up, ready to go for this one. Now, in that Google Drive, I'm including the Python code that we're going to use for this. I saved it as conference test. The other thing you're going to need, though, is you're going to need that data. And I even made it easy for you. I saved the text file in there for you. So you'll notice the name is CH4. That's our methane, MLO, Mauna Loa, surface flask, telling us how they collected it. And and how often they collected it. All right. So if you have that saved in the same file as your Python code, you don't have to tell the Python code much more. It will already know that it's there. So if you download Pathani, you can open up your conference test and your code will be there. And it's going to look something like this. Keep going. Oh, we saw some kids. They were cute kids though. All right. So, now we're jumping around. There we go. Okay. So I'm not going to talk too much about the import because I know Michelle already talked about that, but I do want to tell you a little bit about this code. And you'll notice that my code is even shorter than Michelle's. We don't need a lot of code. So this is a great one to really start with students. You could even start by giving them the whole code. You can even start by giving them the code up to line 20 and having them write those very simple lines of code just to have them work on their graph. So this first piece, line 3 through 8, is really just giving the instructions for importing the data file and describing the columns of data. You notice that there was actually 4 different columns in there. And thank you, Michelle, for putting that in the chat there. The first one is telling us the location. The second is the year. The third is the month. And the fourth is actually the data itself. Now, what gets a little tricky is I told you before the month. It doesn't really work out for us so well with code. So we're going to give it some more instructions later for that. But we're also telling it what file we're looking for. So I have the file just copied and pasted in there under file name. Now, the next thing we need to do, and I didn't get a chance to show you this too much, but there's actually a lot of information before we get to the data itself. They actually give you a lot of background information about where they're collecting it, how they're collecting it, some givens that they're making when they're collecting this data. Now, that's great for us if we're going to write a report and report on all these things. But if we're trying to run a code, we want to tell it to ignore all of that. So this information here is going to tell it exactly what line we're going to start actually reading our code. So we've told it 56. And what's great about this data from NOAA, they tell you that right at the top. You don't even need to go in and count the lines. They give you that information. So the next piece here, so line 9 through 13, is actually going to help us split up those columns of data. We don't want it to read it in one line. And what's tricky is you'll notice there weren't any commas between each number. So we have to kind of tell it exactly how we want to separate this all out. After that, we need to give it a little more instructions. So remember I told you we had those numbers for the month. We're going to actually turn the months into decimals and make it a little easier for it to read. And so that when we graph it, it will graph correctly. And it's also helping us to assign data to our X and Y axis. After that, it's going to start actually printing out our data, our methane, as well as our month, year as a decimal. And the last piece here, and if you want to start working on coding with your students, this is a great place to start. This is actually giving the instructions for printing the labels for the graph and telling it to plot the data. So this is a pretty simple way, and the students can make their own labels because hopefully they remember how to write a graph from some of their earlier math classes or science classes too. Okay, now we ran our code and it looks something like this. Now, this was great. I don't know about you. I would not want to by hand try to build this or even do this with Excel. There would be a lot of data. And it ran this for me in just a few seconds and printed out this beautiful graph for us to use. And now looking at this data, we can start asking some questions. So we're going to jump to the next slide and asking simple questions, right? So what do you even notice if we're talking about methane over time? What can we learn from this graph that we could not learn from the text file, right? Now, it's pretty obvious, right? Our methane is increasing over time. Now that we can see this, we can really see that it is going up. The next thing too is it's interesting once you see it this way. And I know for the number of times I looked at this data, I never noticed this until I had this great graph here. Why is the data oscillating so frequently? All right. It's going to have to do with seasons. It's going to have to do with what's happening in that local environment. The next thing that you could probably ask, right, is why is the methane concentration increasing over time? That'd be a great conversation starter for your students. And that might even be a great homework or kind of add-on question for them to go look into. Now, depending on where this is located in Hawaii, they obviously do not have the same factors we have here in the continental US. So maybe is it something that are they located near farms? It's always a common thing. And one of my favorite topics to talk about with students is cow farts. And if you didn't know about that, you should definitely go look it up, how cow farts are increasing the methane in our overall atmosphere. Are they located near a farm? Are they located near some other source that is increasingly giving off methane? Those are some great questions that you can ask your students, and there's a lot of fantastic answers. And the other question we can ask is, do we think that other locations have similar methane levels? Now, if you notice on here, this is starting at about the 1600 to 1650 range, and notice that we're measuring this in parts per billion. and goes all the way up to the 1950 range in parts per billion. So then I said, okay, we've looked at Mauna Loa. Now we need to compare, right? Is this typical? Is this atypical? Let's compare. So I went back and picked a different location, and this time I went for the continental US. So if you jump to the next slide, I analyzed some data from Point Arena, California. All right. And I took that same code, and there's only 3 simple changes you need to make. The first one, change the file name. We want to make sure we are downloading and importing the correct file for this piece. And I did the same process through the NOAA website, except I just picked a different location. Then I have to tell a different start point. So even though it's the same style file from NOAA, they're going to have different sets of information, and it's going to start at a different point. So this one, instead of 56, it's 53. And then the very bottom, the last and very simple piece, we're just going to change our graph title. Now that we're not using Mauna Loa data, we're using Point Arena data. I'm just going to go in and fix that. The other thing I want to point out is that this data is actually a little bit shorter. This is only from 1999 to 2021. They actually ended this project about a year ago. All right. And if we look at this data, this is very, very different. We have different oscillations. Right now, we also have a much smaller range in terms of our monthly average. We're starting all the way down at 1810 up to about 1890. We don't have huge ranges here, but it's interesting in looking at this graph, it looks like it is. So this is another way to talk to your students about when we're trying to visualize data. So if we put these side by side, it may look like there's actually larger oscillations here, but really there isn't. If we're looking at the measurements itself, they're actually a lot smaller. So this is not a huge oscillation, but there does appear to be an increasing trend here in the methane over time. All right. All right. And like I said before, that is just one database from NOAA. There are a ton of other databases in NOAA that you can utilize. And this code that I had here is in the Google Drive. Go in, please take it. I know something someone taught me years ago is the best teachers are the best thieves. I want you to take this with you, use it. And it's a really great way to introduce your students to data analysis and making them more aware of some of the data we're collecting across the US. And I know Michelle has some other databases that she's going to share with you as well.
Yeah, so Teachers Helping Teachers here, our participating teachers this summer actually spent some time compiling a list of databases that they found during the workshop because they thought that this was just so great because it's easy to fit into, a quick class period. So they found a few other NOAA-based databases. So this list in the Google Drive, if you open up the PDF of the slides, has clickable links. It also has ideas for where each database could fit into a STEM curricula and information on how to access and or organize the data. So there are 2 NOAA databases that they really liked. The Global Monitoring Laboratory that Amanda just showed you, which is mainly pollution data, and the National Centers for Environmental Information, which has a wider variety of data. It includes, but is absolutely not limited to, I couldn't list it all here, but it includes marine biology and geology, ocean chemistry, space weather, climate models, geomagnetism. So like even our physics teachers could be doing this. So it's really incredible that there's just such a big range on that one. So they did really like it. Then the Department of Energy that runs the national labs has the Atmospheric Research Measurement, or ARM facility. This focuses on atmospheric data such as aerosols, clouds, sunlight, and other things like that. Finally, they recommended the NASA Center for Climate Simulation. This has many different options, including atmosphere, land, and ocean data. Some of this even comes from citizen science, from students like yours, where they have apps for collecting data about all of these things about atmosphere, land, and even ocean. So that one's cool because you can get the NASA data from the satellites, but you can also look at some data that was collected by people. And my favorite is that you can access current weather data from Brookhaven Lab at any time using the meteorological, that word is so hard for me, services dashboard. We call them MET services because I can't say it right. This has measurements for temperature, pressure, humidity, rain, and wind at 3 different locations. So at one spot near the ground, another one that's 10 meters off the ground, and another one that's 85 meters off the ground. So it's like really high up there where they're measuring. If you prefer to look at a change over time, like those nice graphs that we just did with Amanda, instead of the current values, there is actually an option near the top of the page. I kind of blew it up here so you could see it. The option called MET-QA/QC has graphs of all of these types of data over the last 24 hours. And there's also an option if you want to talk about solar energy instead of weather and climate. There's a solar base station, and that gives you both current sunlight information and graphs of the sunlight over the last 24 hours. And this is in relation to solar panels that we have around the lab. So lots of options for taking current weather conditions from Brookhaven Lab. And that's pretty cool because actually the National Weather Service station is located at Brookhaven Lab. You may have seen that your severe thunderstorm warnings come from up to New York. So it's a nice connection there that you can get weather data from the place that actually figures out your weather forecast. So it's pretty neat. And of course, we have to do a shameless plug. Speaking of BNL resources, I would like to get near the end of our talk here because I want to leave some room for questions if you have them. I do want to summarize some of the opportunities that BNL has for you and your students. So we encourage all of you to visit us on field trips with your students. We have free sessions for grades 1 to 5 and paid sessions for grade 5 to 12. Those are BOCES aidable if you're worried about cost. And we want you to keep an eye out for more professional development workshops like this one in the future. It's been a while for us. COVID kind of slowed us down, but we'd like to get a lot more teachers in here in the near future. So keep an eye out on our website, bnl.gov/education. If you have any students interested in learning more about STEM, please let them know that we have contests for just about all ages. We have summer programs. Some have fees. Some are funded by the Department of Energy or by the lab. We actually have 2 student summer programs that I would like to point out we have one for 9th grade students. It's called STEM Prep. One for 10th grade students called Rising STEM Scholars. It's a series of programs for students that are underrepresented in STEM. And that will lead into, it's kind of like a guided introduction to a great program called the High School Research Program. That is almost like an internship. You actually spend 6 weeks with staff at BNL working on a project. And that's open to any students that are in 11th grade right now or 12th grade right now. So they can spend a summer even after they graduate with us if they'd like. The goal is to have the students start with us in the summer after 9th grade. If you have these underrepresented students, they can start with us in STEM Prep. They'll grow their STEM skills with us throughout the Rising STEM Scholars. And then when they're old enough for the High School Research Program, they'll get in immediately because they have all the basics that they need. We do cover a lot of coding in that because, as you can kind of tell from my introduction, it's something that's really important to us at the lab. And I also want to tell you about the Spark program because that allows you and your students to work together to perform authentic research because you'll become a user at Brookhaven Lab. So way back in the beginning, I said places like our National Synchrotron Light Source, and there actually are a few others. We have a Center for Functional Nanomaterials. We have a computational science initiative where you can be a user. You can be someone that suggests a great project idea, and our scientists will help you do the research along the way using our cutting edge facilities. Information about all of these programs and much more. We have college programs as well that I didn't even talk about yet. Is on our website. Again, that's www.bnl.gov/education. You can then, if you are in the pre-college realm like us, you click on K through 12 students and teachers, or you can click the link at the bottom of this slide. Again, it's in that PDF to go directly to that section of the website, the K through 12 section. Many of these also have a virtual option, by the way, because I saw a few of us were from places that were not on Long Island. So we'd be happy to zoom into your classroom and guide you through some activities as well, which leaves us with amazing timing, almost exactly 10 minutes as planned. Thank you for listening at this time. We're happy to answer any questions you may have. If we don't get to all of your questions, feel free to reach out to us anytime. Our email addresses are there. And in case you lose that Google Drive link that's in the chat after the session, there's a QR code, and there's also a tiny little link under it that you can click to get to that at any time after this session. So if I can figure out how to stop sharing my screen, we can see you better for questions, or you can see us better for questions. So you can type them in the chat if you have any questions. And just thanks so much for listening.